so it's my pleasure to have him here to give today's distinguished lecture, speaking on the mythology of magma chambers.
Thank you. I got 5 minutes left. Thank you, Miguel.
You have as long as you
I can't tell you how much of an honor it is to be here doing this. I was so pleased and surprised when I got the invitation. And my wife, Mary Alumni, and I came out on Tuesday, and we spent Tuesday afternoon and all day yesterday wandering around the campus and thinking just what a beautiful place this is. And much of it is the same as it was when we were here. And I started here, I did the math, I checked it on the calculator, 50 years ago. 50 years ago I started. And the campus, so did Peter Bird. The campus is very much the same. The trees are bigger. It's really, I can't tell you what a beautiful place it is and how nice it is, and today especially, what a beautiful day. So thanks again. So I'm going to try to get through a lot here. I decided this is a good time to kind of figure out, how did I get here? Why, like, where am I right now? And I thought for the students in the audience and for the younger faculty, I'll talk about some of the decisions I made and how things turned out and so on. So I'm going to give a little bit of a review of my history, and then I'm going to get into the science part. And the science part, if you know anything about what I do, I like science best when what we think we know turns out to be wrong. And I've had several moments in my career where that's happened, and it doesn't make you especially popular necessarily. It doesn't make your proposals necessarily easy to get funded because people say that's wrong. But it's really rewarding on a scientific point. And what I want to talk about today is I want to blow up the idea of the shallow magma chamber. I think shallow magma chamber, I will show you evidence tonight that I hope you'll leave the talk saying, yeah, maybe those pictures of volcanoes with big red blobs of magma under them are wrong. I think it's a pretty compelling case. It's so baked into our DNA as geologists. We've seen it in kids' books, we've seen it in textbooks, we've seen it in papers and journals and so on. And it's hard to get that out of your retina, but I think it's wrong. So I'm going to go through that. So, why do we care about this? Well, this is a volcano. This is Fuego in Guatemala, and sometimes these things erupt. And they throw out magma, and that's undoubtedly magma. It's thrown up into the air. You have pyroclastic stuff coming down onto the flanks of the volcano. You have fine ash blown up high. You have gases. You have everything else. And that magma comes from somewhere. And it's always been assumed that it comes from a shallow bulb, basically connected to the surface by a pipe. That's what the pictures look like. And eventually it blows out. And that's what I want to question. So what I would like you to do is stare at this blank sheet for a few seconds and imagine a volcano with a magma chamber under it. Okay? Just kind of let your imagination run wild. And I'll bet you'll see something that kind of looks like this. This is the National Park Service version. It's kind of funny. The volcano looks like a jelly sandwich. And the crust here is bird's eye maple wood. But it gets the point across that there's this scary red thing underneath the volcano there. So I'm going to get to that, but I want to go through a sort of a brief summary of how my career evolved over the last 50 plus years, 54 I guess. And I need to get through a lot. Anybody here seen the movie Team America World Police? Oh, yeah. How do you get through a lot of stuff fast? You do a montage, right? Even Rocky needs a montage, so let's do a montage. I grew up in Upland, 45 miles east of here, the base of the San Gabriels. I took this maybe 5 years ago on a nice clear day, and occasionally when I was growing up, it looked like this when the Santa Anas were blowing, but most of the time, it looked like that. This is me on top of Cucamonga Peak, which was in the last picture, and that's the smog that buried us in the 70s. Let's hope we're not heading back that way. Anyway. I loved chemistry. I loved the outdoors. I loved going out to the Mojave Desert and looking at mines and stuff. And I decided on the first day of college that I was going to be a geology major. So here's my cohort of geology majors. That's me on the right there. I ran track for a while, but I couldn't pass my classes and run track, so I dropped track, which was a good decision. This is kind of a funny picture I found. The two people on the left are John Christie and John Ertl, who were both structural geologists on the faculty here when I was a grad student, but they taught at Pomona College for a while. The guy on the right is John Shelton, and the guy in the middle is Donald McIntyre, who had a tremendous effect on my life, on my career, because he kind of took me under his wing, and things he taught, he'd walk into class and talk about whatever he thought was interesting, and some of those things took off. And one day he said, and this was early 70s, so plate tectonics was just gotten to the point where people said, yeah, I always thought that was true. And he said, you know, andesites only occur in subduction zones, and there are andesites all over Southern California. And I went, wow, that means there was a subduction zone here 20 million years ago. I looked at a geologic map, and there's all this stuff in the Mojave Desert that no one had ever looked at, so my senior thesis was to go out and sample those andesites, and I was going to calculate the dip of the subducted slide. It's kind of naive stuff, but it was a great little project. I went out, even found Andesite Avenue in Roswell. Unfortunately, it's no longer there. It's been subdivided over, but I really like that. I would go out there and camp with my girlfriend, and we would, run out of water and have death marches and stuff, but sampled the rocks, and there's all kinds of interesting stuff, and I worked on that. And I wanted to continue that for graduate school, just beautiful Miocene volcanic and sedimentary rocks, and I wanted to continue that for graduate school. And I had earned an NSF fellowship, so I kind of had my own money. And the place I should have gone was UC Santa Cruz, because Jim Gill was doing exactly tectonics and andesites. Had I gone there, I would have done my thesis on a tropical island somewhere. But I decided to come to UCLA, where nobody was working on what I was interested in, because I didn't want to be too far away from Pomona College, because my girlfriend still had 2 years left at Pomona. So I did that. Came in 1976. UCLA was a really different place back then. It was much smaller. Okay, this is 1979. That's Royce Hall. I want to point out the Arroyo, some of you may not know, we're right here right now. The geology building is right here. The parking deck is built on what used to be this arroyo. I guess they filled it in really well because everything didn't collapse. The Northridge earthquake, the Bunch Hall, the Waffle Building, is on that arroyo. UCLA was quite a different place back then, the department was. It was very field-oriented and was very petrology-oriented. So I joined my cohort of other... That's not the right photo. This is Peter, that's you, right? In the beret. So I was extremely fortunate that I arrived in fall of '76, and there was a field trip that fall. The department had a tradition of student-led field trips. And the gentleman in the blue shirt here, raise your hand, Steve. Steve Lynch, graduate student at the time, led this fantastic field trip to Owens Valley, the land that John was talking about, 395, from Bishop up to Mono Lake. And my mind was blown by the geology and the scenery, and my eyes were real big. We'd never gone up there on a Pomona field trip. Here we are at Devil's Post Pile. We had like 80 people on that trip and a giant convoy of old vehicles, and had the best time. And there were other field trips. This is one that Mark Cluse and others led to the Franciscan out at the coast. And then Bruce Bilodeau and I ran one to the Mojave Desert. And I emphasized that at the time there was this tradition of student-led field trips. The guide on the left is the 3rd edition of Steve's book. He still has those for sale. If you have any interest in that area at all, buy one while they still exist. There are some flyers on the table outside. And I really encourage you to pick one up, and Steve will get it to you. The one on the right is one that my office mate Bruce Bilodeau and I wrote 4 years later for a field trip to the Mojave. And this guidebook, I'll talk more about that in a second, led to these geology underfoot books. What happened was I learned a lot about my knowledge of Southern California geology came from Bob Sharp's Roadside Geology of Southern California. And I learned so much from that, and it covered the Mojave Desert and up to Death Valley and all, but it left out Interstate 40. And a lot of my work and a lot of this guidebook, the one Bruce and I wrote, was along Interstate 40, and I sent a copy of it when I was an assistant professor in the mid-'80s. I mailed it to Bob Sharp, who was 43 years my senior at Caltech, and said, if you ever do a new edition, use any of this you want. And he wrote back on a letter, okay, 1980, whatever. And he was the nicest guy. He'd fake this gruff voice, and I could just read his letter and hear his gruff voice. He said, I don't want to write another roadside book. I want people to get out of their damn cars and go look at stuff. And that's what he wrote to me. He said, I've been thinking about starting this new series. Do you want to join me and do it? And this is this super famous Caltech guy. I said, sure. And so we wrote that, where's Patrick, that book that he held up. And that's what came of it. And I learned that style of writing from Bob. He wrote, and he would criticize, he would send stuff, because I would write stuff, mail it to him, and it'd come back bleeding. He'd say jargon, and he would say, that's insulting. Like, I remember one time I said something about using the arcane tools of geophysics, and he said, oh, that's insulting to geophysicists, you know. And I learned a lot from him, and it was a fantastic experience working with him. So this is a group photo from the trip that Bruce Bilodeau and I ran. That's Bruce right there, that's me, that's my girlfriend right there. There's Peter Bird, and there's Clem Nelson. And lots of other students to mention. Let's see, Bart Cluse is right there, I think. Bill Carlson's there, Bob Luth, a lot of other people. I want to take this time just to mention some of the many people that influenced my time here. Like I said, UCLA didn't have faculty doing what I wanted to do. I just did my own thing, but the faculty were so good, and my cohort of students was so good that it was the best place I could have gone. So I want to thank Art Montana, my advisor, Gary Ernst, Wayne DeLacy, Jerry Schubert, Peter Bird, Clem Nelson, and also Ian Carmichael from Berkeley, who came down for 2 quarters and really, I learned a lot from Ian. He really influenced me a lot. And fellow grad students, Bruce Bilodeau, Lang Farmer, Steve Lipsche, Steve Ehrenberg, Mark Cluse, Bill Carlson, Bob Luth, all of these people. So the plan to stay close to Pomona by my girlfriend worked well. She started at UCLA Med School in '78. I finished my Ph.D. I got a job at UNC. We got married, went on a honeymoon, camping honeymoon, and we're still together. She's right there. Raise your hand, Mary. Be here without her support and help and everything else. And also, we have a new granddaughter, so I just, so anyway, life is good. So I continued working in the Mojave Desert for my first years in UNC throughout the 80s, and by the 90s I started, for geologic reasons, working farther north up into the Sierra Nevada, and the access, no more dry camping in a wash, now was rigorous backpacking into the John Muir Trail and all, and the scenery was a little different from the Mojave. And it turns out that nobody had ever done any detailed work in Yosemite. Everybody thought the USGS had done it all. They haven't. And so I started working in Yosemite National Park. I feel so fortunate to have gotten into that and doing field work in places like this. I got to actually do some data collecting while climbing on several routes. And here I'm following Roger Putnam, who I'll mention later, of Snake Dyke on Half Dome, and that was really fun field work. It encouraged me to learn to fly and get the geologic perspective. This is at the Bishop Airport, and you see things from the air that you just don't see from the ground, and so that was really fantastic. And speaking of flying, I somehow got invited to help teach the 20th class of astronaut candidates geology. And So I did that for a couple of years, and then I had 2 different astronauts as field assistants in Yosemite for a week each. And this is Kjell Lindgren, who was an emergency medicine physician, became an astronaut, has kids and all, and to all of those accomplishments and 2 long-duration missions on the space, around the space station, he can add co-authoring a paper with us on granite in Yosemite. So I don't know which of those he thinks is his best accomplishment. So, and a fantastic person, just a great experience. And I always brought students out west for classes. Project-based seminar, and we would come out and do stuff here, and people would always say, why do you take them so far to do that? Can't you do that here? And I'd say no. And I would say Eastern California is the best place in the world to learn geology. And it's true. So, there. Since I retired, I'm working on my book and so on, but I got a gig doing Smithsonian Journeys tours, giving lectures and traveling with them. They're fantastic trips, and here we're in Patagonia last November, and a really motivated group of students here, and it's really, really fun. So I feel extremely fortunate to be able to do the things that I get to do, and then this. All right, let's get to the science part. In the 1970s, a lot of things happened in geology, and especially on the petrology side, igneous and metamorphic petrology side of the science. Plate tectonics was established as a thing, subduction zones and so on. Astronauts were bringing rocks back from the moon. This is Harrison Schmitt, the only scientist to walk on the moon, Apollo 17. He's a geologist. The ocean drilling program. Wow, there should be a ship there. The ocean drilling program, imagine a drilling ship, was bringing back all kinds of data, testing the hypotheses of plate tectonics and all, and UCLA was, at that time, was very heavily petrological. Gary Ernst ran the program looking at the subduction zone, metamorphism, and there were people doing experimental petrology on the formation of these things and all. And the department has completely changed its focus since then, and that's a proper and good thing. It's following where the science is going. So, as I said, I like it when things you think about the Earth or about science turn out to be wrong and revolutions happen. Plate tectonics was one that happened right before I was an undergraduate. All the things we thought about the Earth, continents were static, ocean basins were static and just deep holes full of sediment and so on. Those things all turned out to be wrong. These crazy ideas came out that turned out to be true, and everybody jumped to the new paradigm. So I want to talk about one that happened when I was a graduate student. So let's talk a little bit about petrology to bring everybody to the right state of mind. This is a xenolith, a piece of the mantle, mostly olivine, that was brought up in this basaltic lava. Very rapid eruption from 40, 50, 60 kilometers. Brought this up, and this is kind of a model of a planet. Because this is, if you take out the cores of rocky planets, this is more or less their composition. And if you melt this 10, 20%, it makes this rock basalt. We've known that for 100 years. That's pretty solid. The interesting thing is that the Earth makes more than basalt. This is basaltic magma. You can sit kind of close to it and not get overrun and fried and buried and so on. It puts out basalt like this. This is a sample from Hawaii with big green olivine crystals. And you know, that's very well understood, but the Earth also puts out this stuff, rhyolite, which forms much more explosive eruptions. This is Mount St. Helens, which was not that big on the eruption scale, but you don't want to be sitting this close to Mount St. Helens when it goes off. And if this magma crystallizes underground and cools slowly, it makes granite, which is a good model for the composition of the continents. The continents are thicker and taller, and they're above water. Basaltic crust is below the water. Granite continents are above water. And so this is a very interesting product the Earth makes. This is a gigantic boulder of Bishop Tuff that fell into Owens Valley. You see my students looking. Oh, wait a minute. No, that's a mechanical pencil for scale. It's actually this big. I just took this picture and I said, wow. That's a big rock. So let's look at these rocky bodies in the solar system. Mercury, Venus, as far as we know. Moon, Mars, Vesta, asteroid. They all make basalt. We understand that. The only planet that makes these other rocks is the Earth, which is the only planet that has all this water and has life. Okay? Those things are all tied together. And so how you make this more silica-rich into the spectrum, the rhyolite/granite into the spectrum, is really important. And up until the 70s, the old paradigm for how you did this was crystal fractionation, which means you have basalt magma, and it crystallizes things like these green olivine crystals, and they settle to the bottom of a magma chamber. And the magma that's left behind is depleted in the things that olivine has a lot of, and richer in things that it doesn't, like silicon and potassium and so on. You do this over and over again, and you end up with rhyolite. And if you've ever taken a geology course, you've probably been tortured by Bowen's reaction series, which is a diagram that everybody puts in their book and no one can explain why. Every time I get an intro geology book to review, I say, take this out. Nobody understands it. And they still put it, they say, we have to. People want it. When I was a graduate student, a new idea came out, which is that this high silica end of the spectrum isn't made by this protracted letting crystals fall out. It's made by melting crust that's already there. And in particular, if you melt basalt with some water present, you get rhyolite. And so the paradigm is that you don't get from basalt to rhyolite by this process. You get there by melting this, and it makes this, and everything in between is made by mixing them. And here's some examples of mixed magmas, which are all over the place. My office was room 3711 in the geology building, and one of my office mates was Mike McCurry, and he was onto this very early, and I was one of those people who said, oh, that's stupid. You know, no, that's not how it works, because I was steeped in the old paradigm. When the data I was working on said that this made much more sense, then I jumped to the other side. And during the 70s, there was this big flip to this new way of making the spectrum of igneous rocks on the Earth, and I will return to that at the end. Let's go to Yosemite for a minute. So nobody was working in Yosemite in particular. Nobody was working on the geochemical variations in what we thought were big blobs of magma that had come in. When I was a student, and up until about 2000, well, let me back up for a second. This is a geologic map of the intrusive rocks, the Tuolumne intrusive suite in Yosemite. There are 3 different kinds of rocks. At Glacier Point, you're standing on this kind of dark stuff. Everything in this picture looking east from Glacier Point, almost everything is this half-dome granodiorite that looks like this. And then way in the distance toward Tuolumne Meadows, you get this different unit that has these big pink potassium feldspar crystals. And so this geologic map is just demarcating where these different flavors of, we'll call it granite, live. And the idea up until about the 2000, and the literal textbook idea for how this happened, was that oldest unit on the outside, the one that makes up this purple stippled stuff, came in, a big bubble of magma like a lava lamp came in, started to cool around the edges, and before it had totally cooled, the next big blob of magma, the half-dome granodiorite, came into the middle of that and pushed that molten stuff out of the way. And then before that had all cooled, that last blob of magma that makes that cathedral peak with the big feldspars came in and pushed all of that out of the way. So 3 like lava lamp bubbles coming into each other and making this map pattern. And everybody accepted that. And if you do the math, if you do the thermal problem of how long could that possibly take, it's really hard to stretch it to 1,000,000 years. It's more like 500,000 years, because you have to do it all while everything's still hot. Okay? Now, let's look at some other plutons. A pluton is just a map body of igneous rock like granite. So the White Inyo Range, this is the range east of Owens Valley. So the Sierra Nevada are over here, they're almost all granite. The White Inyos are kind of half granite and half old sedimentary rocks. The granites are in the shades of pink here. And some of these plutons are sitting all by themselves, surrounded by sedimentary rocks. And this is the Birch Creek pluton that Mark Barton worked on when he was on the faculty here. And this is the Sachin Flat pluton that my office mate Bruce Bilodeau worked on under the direction of Clem Nelson. He mapped all of this area here. And these are good to study because the wall rocks are layered. And so like if that came in as a bubble through those layered rocks, it should bend them up like this and drape over the top and all. So these were targets of UCLA. And in particular, here are the older versions of John Christie and Gerhard Ertl that I showed in that weird picture from Pomona College. That's Clem Nelson, and that's Art Sylvester. And Art was a student of these guys, and he mapped a pluton in Norway for his master's thesis, and then mapped the Papoose Flat pluton, which is off the bottom of this map, for his PhD. And then the UCLA had a really big presence in this stuff. And then Bruce Bilodeau, and here's a picture of Bruce in room 3711, thinking about structural data. You notice what's not on his desk is a computer. Can anyone under the age of 50 in this room tell me what this is?
Punch cards.
It's a box of punch cards. Okay? IBM punch cards. Okay, remember that guidebook to the Mojave Desert that I showed you? 1980, Bruce and I thought, let's try this new thing called word processing. We typed that guidebook on punch cards. Took them over across the quad to engineering, submitted them. The next day we'd get the fanfold green and white paper. We'd proofread it, find a mistake. We'd let our fingers do the walking through the book and find the card, retype it, throw it in, do it again.
Each card is 80 characters.
80 characters. A full box of these has 160 kilobytes of information. That's like that's like the old man in the sea, right? Okay. This has 3.2 million times the information storage of that 5-pound box of cards, okay? So for you students in here, things have changed. As you can see from some of the photos I showed, the world used to be black and white. That's another way it's different. Here's a map Bruce made, really beautiful map of this area. This is what it looks like up there if you've ever been to the Crooked Creek Station or the White Mountain Research Station. Fantastic field venue. I use every excuse I can to go there. It's located on the granite right here, and it's tucked in this valley here. And Bruce and I have gone up there for various projects since then. For his thesis, this was the interpretation Bruce had of the intrusion of this granite. So this is the map that's looking down on the earth. These are cross sections cut along here, vertical sections cut along this line. Mary pointed out it looks like a tongue sticking in there. But his idea, following the Yosemite stuff and all, is that the granite ate its way upward through the rocks that were there and kind of stopped when it hit the Reed Dolomite. And when you rode through this at this level, you're left with that map pattern. So I went into Yosemite in the 90s with several graduate students and undergrads. And we thought, well, these are big blobs of magma, so all of these crystal fractionation things that might happen in a big blob of magma should be visible here. And here we've got 5,000 feet of relief from the top of Half Dome to the valley, over 3,000 feet on El Capitan. We're going to do vertical sampling, or as close to vertical as we can get, and look for all the things you should happen. Dense crystals settling, less dense crystals rising, geochemical fractionation, and all that kind of thing. And Roger, he was a little later. He was in about 2010. He was a big wall climber. He's the kind of guy that would climb El Capitan twice in a day or climb El Capitan and Half Dome in the same day. Now he's an ultra runner. I met Roger. He was on a trail crew in Yosemite, and I met him there, and he said, I want to do a master's thesis mapping the southeast face of El Cap. I said, go for it. If you've seen Free Solo, Alex Honnold kind of went up a route on this face over here. The dawn wall is here if you've seen that. But Roger, he climbed about 7 routes, rappelled down several others, and then very creatively crowdsourced observations to other climbers on other routes. And then we made a gigapixel image of the face, and he made this map. It's one of a kind. Nobody's ever done this anyplace else. And I could give a whole lecture on what you can tell in this map, which is available for purchase from the GSA, if you're interested. But nothing predicted by the big blob model fits this map pattern. Nothing predicted by the big blob model fits any of the data any of my other students collected. Did we throw out the big blob model like we were supposed to? No. We figured, these are exceptions or something. It's very hard to throw these things out. Meanwhile, my colleague Drew Coleman at UNC had set up a really precise uranium-lead zircon dating lab, precise as of about the year 2000. And the only dates in Yosemite, not only had people not done the geochemistry in Yosemite, nobody ever really dated them. This is 1994. There was this kind of unpublished report with this scatter shot of ages by all these weird techniques. Some of these ages go back to 1959. And they span like 10 million years. And we said, well, it all has to happen in 500,000 years or so. We'll go in there and find out what the real number is, So we went in and collected a traverse across here, and we got a span of about 8 million years. And we said, well, that can't be right. Did we throw out the big blob model? No. We said, well, there's something wrong with the data. And so we went back the next summer and recollected a bunch and collected a lot more and collected a mirror image on the other side of this and all. Long story short, we got a range of about 10 million years. Within an individual body, like the half-dome granodiorite, we get a range of 3 or 4 million years. And it took us a long time to accept this. And I remember sitting by May Lake in Yosemite. I was by myself that day and writing in my notebook, what if this is true? What does it violate? And I couldn't think of anything it violated other than the prevailing model. And I thought of all these problems it solved. And I went, and that was a big paradigm shift for me. Somehow, we got these data published in 2004. A lot of reviewers said, well, this can't be right. In 2005, we ran a Geological Society of America field forum in Yosemite and Eastern California. We had a full house, 45 people. USGS bigwigs were out there gunning, they were all defending what we all knew, what all righteous people believe, and so on. It was pretty much a hostile crowd, one exception. Everybody else was hostile. So there's me, there's Drew Coleman, geochronologist, John Bartley, structural geologist. The 3 of us ran this thing, standing at the top of a 3,000-foot cliff with our backs to it, facing this hostile crowd. Just making sure I didn't get too close. But it was really a great give and take. And the next year, Berkeley Geochronology Lab went in to set the record straight, and they got the same numbers we did. And it was kind of case closed. And everybody said, I always said that. So these big blob models that were everywhere at that time, they're out of there. So how do these big granite bodies get assembled? They get assembled as dikes. What is a dike? A dike is a fracture filled with magma, or the cooled off remains of such a thing. Here's a very famous dike on the Reykjanes Peninsula in Iceland that fed, it's a good field trip stop, and it fed these 800-year-old lava flows up here. Magma wants to rise. It doesn't rise in pipes. The earth doesn't break that way. It rises along cracks, and that's a magma-filled crack. I really like this one. This is a 20-meter thick dike. It's made of a whole bunch of dikes in Death Valley, and it fed these 3.5 million-year-old lava flows up there. This is near the John Muir Trail. That's John Bartley for scale right there. The dikes form along there. That's how magma moves in the crust. It does not move as blobs. That doesn't work on any level. This is what happened. And you can see this happening. The drone gives such amazing footage now. This is, it's not my drone image, it's from this guy. But this is a dike breaching the surface near the little town of Grindavik, which has been abandoned. That's what a dike looks like when it hits the surface. It makes a curtain of fire. It'll often close down to a single vent. Yeah, we went to Grindavik last June, and it's kind of a ghost town. We think there are dike swarms on other planets, Mercury and Venus, or Mercury and Messenger. That's Mercury. Oh, the Venus, yeah, Mercury and Venus. He's radiating things that look like radiating dike swarms on Earth, like Shiprock here or Spanish Peaks, and so on. On Mars, there are gravens, depressions that are thought to be depressions above propagating dikes below. No field geologies check that, but that's what those look like. So the obvious question is, well, if granite's made up of dikes, why don't you see the dikes? Okay, so doesn't granite just look homogeneous like this? Well, a lot of it does, but what we found, and this is a real scientific point to make, is that we had walked so many field seasons over things that looked like this, and we didn't know what they were, so we didn't pay attention. This is a dike swarm in the granite. This is right near Tenaya Lake in the middle of Yosemite. We mapped it in great detail. It's just a dike swarm with dikes cutting dikes. Older dikes are folded, younger dikes cut the folds. It's just a perfect dilation of this area, filling the space with dikes. And in areas where the granite looks pretty homogeneous, we found that if you take one of these guys, a magnetic susceptibility meter, that you can measure the magnetic susceptibility, and it's very sensitive to the amount of the mineral magnetite, and you can map out dikes magnetically that you can't see. And so granites are just dike swarms. Okay? Now let's get to the real meat of the matter here. Are magma chambers, shallow magma chambers, real? And the answer is no. And why is that? Okay, I'm going to give you 3 reasons. One, plutons, as I just showed you, are not cooled magma chambers. When they were big blobs, it was a big blob of magma, big magma chamber rising up and then cooling and crystallizing. So the fact that plutons were evidence that there were magma chambers obviously they're magma chambers because we see plutons that are frozen magma chambers. Well, we threw that idea out. So now it's like, oh, I can't believe it took me 15 years to start realizing the implications of that. Because it's also true that nowhere on Earth have geophysicists detected a true magma chamber. You may think you've seen a lot of magma chambers in geophysical papers, but this second statement is true. And then I will show you that shallow magma chambers are not thermally viable. And you're thinking, but I've seen so many diagrams of magma chambers, like this one. This was a study, Huang et al., 2015, the University of Utah seismology group did a great study on Yellowstone. And they seismic tomography, and they published this figure along with sent out a press release that said there's enough magma down there to fill the Grand Canyon 11 times. So, and all the preppers went out and bought all the freeze-dried food that there was to add to their stores. National Park Service made this kind of waterbed full of magma figure here. You stomp on the surface and you think Yellowstone would kind of go like this. But if you read the paper, and it's a good paper, if you ignore the press release and read the paper, they say that this thing up here has maybe 9% melt, 91% crystals, and this might be 2% melt, 98% crystals. That is not magma. Magma is something that can flow and move and be injected into fractures and erupt. If you have something that's 90% crystalline framework, that's a solid. That's not going anywhere. It's got melted little pockets in it. So they call this magma. It's partially molten rock. It is not magma. And nobody has ever found reliably a volume of the crust that has more than 50% melt. Early in plate tectonics, mid-ocean ridges where the plates are spreading apart, people thought that there were big magma chambers. This is about 5 kilometers tall, 5 kilometers wide. To me, that looks like an alien reptile tongue in cross-section. And marine geophysicists said, let's go out and find those and map out their dimensions. And they went out, put out ocean bottom seismometers, shot off air guns and things, shot seismic waves through there, and they could not find them. They're not there. The best they could do was maybe find little lenses a few hundred meters thick, but none of these giant bodies of magma. And so they said, okay, they're not there. If only land geologists had done that. Land geologists, instead of saying, okay, well, they're not there, they doubled down. And the buzzword now is transcrustal. So in 2017, Cashman et al. Published this. Wes Hildreth followed up with one like this, where these things are basically molten from the crust mantle boundary almost to the surface with magma bodies all over the place. So I looked at these and I thought, I wonder how much energy it would take to build one of those. And so I did some calculations, and I really thank Jerry Schubert for the class he taught when I was a graduate student. It gave me the knowledge and the confidence to do these kinds of calculations. I would not have done that without Jerry. So in this paper here, they said, well, this is the initial geotherm. This is the initial increase of temperature with depth. That's kind of similar to what it is under our feet right now. You might get 600 degrees Celsius at 50 kilometers. And the mature geotherm of this system is like this. So I said, how much energy does that take? And it's very simple to calculate. It's a simple integral of the heat capacity times the density times this temperature difference. So for this system that they proposed down to 50 kilometers, that integral is about 5 times 10 to the 13th joules per square meter, which is about 1 gigajoule per cubic meter. And the only thing you've got to raise that temperature, there are no heating coils, there's nothing but magma. The only thing you can do is bring in magma. You can't stick magma down here because that would take 100 million years for the heat to get up there. You got to inject dikes everywhere to heat this up. How much do you need? 20 kilometers. You'd have to add the salt magma equivalent to 20 kilometers. You'd have to increase the thickness of the crust from, say, 50 to 70. And we can absolutely rule this out. In these volcanic areas, the crust is not noticeably thicker than it is outside. So we can just rule this out based on the, and somebody tell me what's wrong with this calculation. Nobody has. People that don't like it, ignore it. So if you're sitting in a bar sometime, talking to your friend, or some random person, and you say, shallow magma chambers probably don't exist. And they say, oh yeah? Just pay attention, do this. Get a cocktail napkin. Borrow a pen from the bartender and draw this. So everybody draws their magma chambers to the top at 5 kilometers. So draw this little thing and say, what does it take to keep this alive if I'm bringing in 1200 degree magma? Well, to keep it alive, the heat in has to be at least as big as the heat out. And I won't go through the details, it's pretty simple to do, but I define this dimensionless number that's just the heat in the numerator and the heat out in the denominator. And if this is greater than 1, the magma body grows. And if it's less than 1, then these new inputs of magma just freeze and you make a pluton. And long story short, in this one-dimensional problem, you get to keep this alive at 5 kilometers, you gotta thicken the crust by adding enough magma to inflate the crust by 10 kilometers per million years. It's 10 millimeters a year, which doesn't sound like much. That's 10 kilometers in a million years. So these magma bodies that people draw pictures of at 5 kilometers that are sitting there for 2-3 million years, like building up to Long Valley or something, you'd thicken the crust by 30 kilometers. This is a one-dimensional calculation. There's no cooling out the sides. In the paper I wrote on this, I did the 2-dimensional calculation, which is slower than an actual 3-dimensional. And you get like 16 kilometers per million years, or 20. The only way to solve this problem is to put your magma body much deeper. If you put it much deeper, then the thermal gradient above it is much less, the heat loss is much slower. magma bodies can live down here. They can't live up here because there's no evidence of this putting this kind of mass of magma into the crust. Now, interestingly, on some other volcanic bodies in the solar system, this argument doesn't apply. The cryovolcanoes erupting brine on Saturn's moon Enceladus, and the sulfur, I guess, silicate volcanoes on Io, orbiting Jupiter, don't have this problem because their heat is supplied by tidal bulges, by tidal forces on the planet, basically heating it like a ball of putty. So these arguments don't apply to those. And there are a bunch of other things wrong with this concept of, that, this is the diagram came out when I was a grad student, this big magma chamber under Long Valley. This basalt, andesite, dacite, rhyolite spectrum of igneous rocks. They don't explain the time sequence of variability of volcanoes, and they don't explain how magmas can mix so thoroughly. So I mentioned mixed magmas early in the talk. This is one of the first rocks I collected as an undergrad from the Mojave. These are big quartz crystals in an andesite. Andesite isn't supposed to have quartz in it. These are all plagioclase crystals that are grossly out of equilibrium. This is a very clear magma that's a mixture of basalt and rhyolite. You find these all over the world, and they're always really thoroughly mixed like this. And to get back to UCLA, a bunch of people at UCLA pioneered single crystal isotopic analyses. John Davidson and Mary Reed were faculty and grad students. Frank Ramos, Kurt Niesel, and Frank Tepley did this. And these are from some rhyolites in New Mexico. And just take my word for it. These are strontium 87-86 ratios from a single magma. They should all be the same. These are gigantic variation among the crystals in these rhyolites. Gigantic. Many sources in that lava flow, or tough. How do you mix things like that? How do you mix these magmas together? This is a big magma chamber convecting, and that's all you got if it's a magma chamber. You got convection, and I don't see how you can get thorough mixing like that. I've recently got onto this idea that, I'm surprised I didn't realize this a long time ago, and I'm just about done. This is a dike. Here's the wall rocks. Magma's going to flow from the bottom to the top, and let's just assume these numbers are meters. So it's 2 meters wide, and this is 10 meters downstream. And this is the velocity profile. It's 0 at the walls, and it's highest in the middle, and it makes a parabola. Everybody knows that. This is called Poisson flow. Everybody knows that's the velocity profile, okay? It only occurred to me a couple of months ago what that means downstream. So I'm going to show you a little simulation. So these are 6 little packets of magma, 20 centimeters on a side. These are at the starting line at 0, and these are behind them, 80 centimeters behind them. Watch what happens as they flow downstream. So the 2 packets in the center aren't very deformed, and they're still a meter apart. But these packets get smeared into these really long, skinny things. These packets that were 20 meters on a side at the start down here, the blue one and the red one, are now 4 meters long and a centimeter thick. And they're 4 centimeters apart. And this is for 10 meters of flow. Magma might flow 10 kilometers. These things would turn into thin little ribbons. And when they're flowing through real dike complexes, which can be pretty complex, I think this is your mixing path. This is how you mix things together. Dikes flow along, they pick up different magmas, and they all get in there and get incredibly smeared out, and you end up producing the kind of mixing that gives you magmas like this. These are mixed magmas, Oregon, and then 1915 eruption of Lassen. And when you smear these layers down to the crystal size, millimeter scale, the crystals in these shear magmas are turning, and they're actually tumbling and doing all kinds of things and dragging one layer into another and so on. And these kinds of mixed magmas are not that common in the world. And I thought that's because, well, this kind of mixing doesn't happen very well. Now I think just the opposite. This is really common, and the only time you preserve this is if if it freezes right at the start, before things have flowed very far. So all these mixed magmas, you flow this 100 meters, 1,000 meters down the conduit, and they get mixed into homogeneity. And you don't see this unless you take it apart isotopically, the way that Frank Ramos and others have done. So I think we can view, say, a stratovolcano like Mount Rainier or something. Instead of having a blobby magma chamber up near the surface, which we never see and are thermally unworkable, that we can have partially molten zones. Maybe these are magmas, maybe they're just partially molten zones fed by basaltic magmas coming up from the mantle, cooking these things up, and then this more evolved magma erupts to form the stratovolcano or whatever, and you might get mixing between the basalts and the more evolved stuff here. So I think everything that magma chambers were supposed to do but actually don't are done in dike networks like this, and this is the next revolution I would like to foment. I gave a talk about this at GSA a year and a half ago, and there were people in the audience going like this. So that's the kind of, because we all have those pictures in our head, but I think this is true. You may be asking, what about big caldera forming eruptions like Long Valley? You erupt 1,000 cubic kilometers in a week like Long Valley. It has to be a magma chamber. It's just not here, it's down here. I'm working on the drawing. Actually, I have one, but it slides away, so I'll leave it here. But it's not thermally viable here. You can't keep it alive if it's 20 kilometers down, and I don't know of any data that contradict that. So that's the next thing to work on. So that's a lot. Thanks for sticking with it, but that's the main idea. It's been fun to come in on right after revolution happened, to be a graduate student when it was happening, to cause one to happen, and then in my waning years to hope another one happens. So thank you very much. I appreciate it. Thanks for your attention. And
All right, any questions for Alan?
Thank you so much. I actually have a question about this. In this cartoon drawing, are the dikes converging? Like, you've drawn them sort of converging in the actual world. Do you see them converging, or do you see them like sort of everywhere but then a certain flow pressure?
I drew them that way. I actually had them closer together, and I actually grouped everything and stretched it horizontally to emphasize this. I don't know, fluids flow down the pressure gradient, and I like to think of this as kind of like a prison break. Like if something makes it to the surface, the pressure releases, everybody goes, hey, there's a hole in the fence. And they get to it. I don't know why the footprint of magma scavenging can't be significantly, well, it's got to be bigger than the footprint of the vent of the volcano. So I don't know what would limit that.
That's concentric circle instead of.
If it's in an area where there's crustal extension, which a lot of volcanoes are, it could be elongated perpendicular to the stretching direction. And it would be nice to take a planet and take a volcano and just cut it like this, but we have to reconstruct. We do forensic work trying to reconstruct. You know, if you find volcanoes laying on their sides, like in the basin range where they've been stretched out, you have to reconstruct it. So, but it tells you something to look for. If anybody thinks this is worth pursuing, it tells you something. It's a very good question, and it's something to look for.
Yeah, a great talk, Alan. The volcano that I'm most familiar with is Kilauea.
Is what?
Kilauea. And when that's about ready to erupt, they have tilt meters that are moving, they have earthquakes, everything is working. And I don't really see how using dikes could create that kind of phenomenon.
Well, before the things start tilting and all, they start seeing earthquakes as the magma's moving
That are
from
that
deep.
deep, but they're very deep.
They're
The
very deep,
epicenter
but
is
they
deep.
can see them rising up, and they can kind of predict when it's going to load up. So
That creates an earthquake.
the dike
Moving through a
propagation.
dike creates enough of a resistance for an earthquake?
Well, there are different kinds of volcanic earthquakes, but if it's breaking the rock, it does. If it's flowing through a channel, you get so-called volcanic tremor. Any seismologists here?
Well, I'm not a seismologist, but there have been studies where they can trace the earthquakes caused by dike rejection.
Oh yeah, in Iceland.
Yeah, that's.
And I actually wrote a paper tying the B value, the sort of fall off with intensity, to dike thickness statistics. It was kind of fun, and it gives the right B value for volcano. Question is, you know, a lava lake is a magma chamber, kind of. You know, you fill up the throat of Kilauea and then, or Mokuauea, or whichever caldera you want, put a crust on it, you call that a magma chamber. Clearly, there's a small balloon of magma that pumps up under Kilauea, and then it shoots a dike out these drift zone vents. So that's that kind of edifice inflation where you're just kind of pushing the crust out of the way temporarily, lifting the surface temporarily. We can call that a magma chamber, so I should maybe not be so dogmatic in saying shallow magma chambers don't exist, but that's like a little temporary storage area.
And this accounts for the caldera sinking after that
In
magma is gone.
Yeah, and that's a small example of that. Galapagos do the same thing. It's the bigger ones. I think there's something fundamentally wrong with the way we think about how caldera is structured, and that's a different talk. But I'm pretty convinced by that. So there are little calderas like Kilauea and so on, and pit craters, and then there's Long Valley and Yellowstone and all. Yeah. I don't have all the answers. Yes?
So one of the observations you started with is how common the structures that we interpret, or we call these zoned plutons are, and you know the model that was for a long time, you know, the progressive crystallization inward. Why do you think this structure is so common though under this model?
Like getting more silicic inward or whatever?
Yeah.
So the way, the structure, I think most shallow plutons that aren't sheeted dike complexes, some are clearly sheeted dikes with wall rocks in between. Ones are kind of bulbous, are basically shallow lackless. They're basically shallow intrusions that are more pancake shaped. When you have layered rocks, like on the Colorado, I have a slide I took out because it would take too long. If you're on the Colorado Plateau, you're in all these flat sandstones, and then you see a mountain in the distance. That mountain, if you see a mountain in the distance that isn't a long ridge, a fold, it's a lacklith. A lacklith is where magma comes up dikes, and it takes a lot of work to break the rocks ahead of an advancing dike. And if it gets to within a few kilometers of the surface, it goes, you know what? It's going to be easier if I just lift everything up and spread out this way. So the La Salle's near Moab, Navajo Mountain near Page, the Abajos, what's the one near?
Henry.
Well, the Henrys are, yeah, the classics, thanks. Sleeping Ute, all these mountains on the Colorado Plateau are lackless. And I think Yosemite is lackless. We think the best structure for Yosemite is a bunch of shallow sheets that were intruded one under the other. So once you form a granite body or an intrusive body like that, it makes a hard, and this is shown in experiments too, it makes a hard barrier. So magma coming up is more likely to sill out underneath that. And if you arch that a little bit, then you get that concentric zoning. So it's thinking of, instead of being concentric zoning that is vertical cylinders, it's concentric zoning produced by cutting through a series of shallow sheets.
One
That
last
makes
question.
sense.
Sorry.
Can I ask you, have you ever looked at exterior created shafts and area under the lower down that are created by water or other phenomena that would allow these mold or other stuff to come up?
You mean like the LA subway system?
Well, yeah, but I mean, you know,
That
over
was a
time,
joke.
and I lived off 395. I had an address other than a golf ball over there for many years working, and I've seen I do prospecting, and I get a concept that a lot of the waters and subterranean created cavities could be the most likely avenue for the being able allowed to have crust.
Yeah, but you know, this is to scale, that's a 3-kilometer
Yes.
stratovolcano, and those would be in this very, very upper bit.
But there's never any cavity below the crust at all?
Below the shallow crust, where you have open fractures.
Yeah. I mean, couldn't, coming from exterior to create some of the shafts?
Well, the exterior forces that do it are crustal extension, where the crust is being stretched by usually plate tectonic forces, and you're breaking fractures, and that's, volcanism and stretching of the crust are really associated worldwide. It's not one-to-one, but it's pretty close. So that's, I think, the closest equivalent to that. You can't hold something open when it's under kilometers of rock. Yeah.
Okay, on that note, let's